area of a polar region. So we're going to go through the theory of it, and then we're going to just do this example. Well, first we're going to motivate the theory by this example. R equals 4 sine 2 theta. And that graphs from 0 to 2 pi, you get the whole figure with all the 4 leaves there. Okay, now let's see how that's created. So here's your R equals 4 sine 2 theta graph, and I'm going to just go ahead and animate it here. It's graphing for these radian angles until you get to 1.57 approximately. That's pi over 2. So pi over 2, it did complete one leaf in the first quadrant, sorry. And that is just, it always doesn't work out that way, because we've seen on R equals cosine theta that the whole circle was graphed just going to pi. So you got to be careful about this. Then continuing on into second quadrant angles, notice that the leaf starts tracing out in the fourth quadrant. That means the R's are negative. That means that when we have values in the second quadrant, the radii were shooting backwards and tracing out the curve 180 degrees in backwards. It comes up to 3.14 right around here. So we completed 2 leaves. Now we're beyond pi, going into the third quadrant, and we're graphing in the third quadrant. So those radii are positive, and we're going around. Then we're stopped here at about 4.71 something. That's about 3 pi over 2. Now we're going to have angle values beyond that going into the fourth quadrant, but we see our leaf is tracing in the second quadrant, which means the radii are negative from the function. So we're shooting backwards, graphing backwards into the second quadrant. And then we finish up 2 pi, and the figure was rendered. So we got to be careful about our boundaries, because just because we went around the circle, the quadrants one time, and finished up the figure, you don't know if you just see the final graph whether you've graphed it twice or not. So you really got to be careful about your beginning values and your ending, and making sure they're just tracing what you want to trace one time. Otherwise you might get double the area when you're trying to get that. So as we've just seen, this leaf right here does indeed trace out all this area and covers all this area in there, indeed, as the angle traces from 0 to pi over 2. Okay, so that's what we want to find. So now the theory. An area of a sector of a circle. You have the area of the entire circle, and you want a fraction of that area. So if this theta here was like, 1/4 the way around, it's pi over 2. That would be pi over 2 out of 2 pi, or that cancels out to be 1/4. You'd get 1/4 of the area of the circle, and you can see that's a first quadrant, so you would get the area of the 1/4 the area of the circle. So this is your formula here, and then how that relates to what we're doing is we would cancel out those pi's, have a 1/2 theta r squared as the area of a theta sector. Of course, we're doing calculus, so we're going to be concerned with small delta theta, but it's still an angle. It's still a very small angle. So over on this picture, if we were trying to find the area of this sector in there, all that stuff right there, going from an angle theta to then theta plus delta theta, well, your delta theta would be that angle there, and so you'd be wanting to have a sector, and you can see it'd be like a part of a circle if delta theta is very small. So your delta theta sector would be 1/2 delta theta r squared. So there's your little formula for the delta theta sector. Now in our example, the delta theta sector would be for r is equal to 4 times sine of 2 theta. So we would put that in there for the r, and that would be the area of a delta theta sector. And then we would want to add all those up to get our one leaf. We know that the leaf finishes up from 0 to pi over 2 and completes this one leaf in the first quadrant. So we would just sum those up, and of course that becomes an integral when delta theta goes down to 0, and here you have it. There's your area of the leaf. But then, we're going to do this by hand and with the calculator, so we're going to multiply this out. 16 1/2 sine squared 2 theta 0 to pi over 2 simplifies down to this, which on the calculator is 6.2832. You probably recognize that number, and that was using Simpson 100. So that might be done if we were just going to use the calculator, and plenty of problems on a test would be like that. But if we wanted to figure it out and we were required to do that, then you'd be using it's sine squared up there, and there's a reduction formula for that, the sine reduction formula, which you have on your sheet. So it's right here. But we have a 2, very buggy 2 in there, so we got to sub that out. So here's your substitution method to sub that out. We're going to convert the limits over to the u limits, and then convert everything over, and you end up with this. Okay, so our original integral is 8 times 0 to 2 pi over 2. So we have our original integral we're trying to figure out. So there's your 8, comes there. And then this integral in here is 1/2 0 to pi, like this, which is 4 times this. So that's where we are right now. So now we're just going to concentrate on this integral here using the reduction formula. So n is equal to 2. There's your 2. So n is 2 there. And everything, computes in there. Just plug everything in and you get the answer right here. Of course, it's n minus 2 is 2 minus 2, which is 0. That's why that's there. Of course, that's just 1 sine to the 0 power. And this was n minus 1. 2 minus 1 is 1. That's why that 1's there. And simplify it down and you get this. But our original integral we wanted, the use substitution version, was this, so we want an extra 4 multiplying there. And evaluate it at 0 to pi. You evaluate, do all the evaluation, and indeed it comes out to be 2 pi, which does verify with our Simpson approximation from above. So that's good. That means we did it right. Okay, so the area in one leaf of r equals 4 sine 2 theta is 2 pi. That's pretty interesting. It doesn't look like a circle. It isn't a circle, but yet the area turns out very nice. So in general, the form for getting the area of a polar region is this right here. And you just got to be careful about your limits, because remember, you can double trace something or quadruple trace, and when you're looking at the final version of the graph, you don't really know that you've traced it twice unless you check it. So that's going to be important.